4 cubic yards of concrete every 3½ minutes, the high-level mixing plant at Boulder Dam represented the ultimate in plant installations of its kind. Here, automatic equipment not only controlled the apportionment of the concrete ingredients, but in addition maintained a graphic record of every plant operation. From his post on the control deck of the mixing plant, an operator was able to direct the entire mixing cycle, from the initial weighing of the ingredients on through the complete mixing process. The human element was almost completely eliminated, as the mechanical equipment was capable of automatically selecting, measuring, weighing, and recording the proper materials in the precise amounts required for the production of a given mix, to which the recording dials had previously been adjusted and set. Here also we find the production line conveyor belt speeding up the process by carrying the component parts from the measuring and weighing hoppers into the batching bins, from which the materials were dumped into the 4 cubic yard capacity rotary mixers. Water was added in controlled amounts, and the entire mass thoroughly agitated as the last step in the economical and efficient manufacture of a concrete strong enough to withstand the enormous pressure to which the dam would be subjected. From the mixing plant, concrete was dispatched to all sections of the works, and because of the widely varying conditions prevailing, various types of containers and methods of transportation were involved. Motor trucks and electric trains were utilized as carriers, and containers varied from the 8 cubic yard capacity bottom dump buckets to the 4 cubic yard capacity transit mixers. The latter were used on long hauls, where it was necessary to agitate the concrete in transportation to prevent segregation of the mix. However, the major portion of the concrete handled on the project was carried in the 8 cubic yard buckets and transported from the mixing plants by electric train. A system of 9 aerial cableways spanning the canyon from rim to rim and anchored at either end to movable towers was utilized to carry the concrete and other materials from the points of train or truck delivery to the dam and other structures on the project. It was on June 6, 1933, that the first bucket of concrete was placed in the very lowest of the dam forms, 135 feet below the level where a few months previously had flowed the unchallenged Colorado River. What was to become the highest dam in the world began to rise from the impregnable rock of its foundation. As bucket after bucket of concrete was dumped into the forms, the plan of the structure became apparent, and soon extended along its full 660 feet dimension of thickness at the base. Throughout the lower levels of the structure, concrete was placed from a trestle anchored to the Nevada wall of the canyon. The concrete was poured in keyed or interlocking columns, the design of which became more noticeable as the 5-foot layers or lifts in which the concrete was placed rose from level to level. As the work of placing progressed, the crews became expert in the handling of the equipment, and record-breaking daily pours were made, only to be surpassed by later achievements on this same structure. Transit mixers were transported on trucks, from the bed of which they could be removed and handled on the overhead cableways. These were used in the placement of concrete in the confined forms along the abutments, where the 8 cubic yard buckets could not be handled. Selecting at random one bucket from among the hundreds of thousands that traveled from the canyon rim over the cableways and down into the dam forms, we see the typical operation from the time the bucket is picked up by the cableway on the canyon rim, swung out into midair over the gorge hundreds of feet above the forms, its tremendous weight of 22 tons riding easily and gracefully over the cable, as it is lowered into the forms with an ease and certainty seemingly out of proportion to its great bulk and tonnage. As the bucket descends, suspended at the end of hundreds of feet of cable strands, it is received at the forms, the safety locks unlatched, the signal given, and 8 more cubic yards of concrete added to the dam's bulk. Concrete was compacted into the forms by mechanical vibration, the application of which ensured dense compression against adjacent surfaces. Workmen were carried from the canyon rim to the dam forms by way of the inclined skidway, or monkey slide as it was called, which operated through the Nevada abutment excavation. Boulder Dam laborers represented a fair cross-section of the American working class, and many stayed on the job during the entire period of construction. With an ambitious progress schedule to meet, and with work going forward under all conditions at all seasons of the year without cessation, rain or shine, both day and night, Within a year, less 4 days, 2 million of the 3¼ million cubic yards of the dam's total volume had been placed in the forms, and Boulder Dam had risen to an impressive height, already having taken its place as one of the wonders of the West and a tourist attraction of prime importance. Meanwhile, progress had been made in the erection of the structures appurtenant to the dam itself. The construction of the power plant, a U-shaped structure at the downstream toe of the dam, had been in progress for some months, and as its substructures assumed form, it gave some hint of the beauty it was later to possess. The intake towers, 2 on each side of the canyon wall immediately upstream from the dam, were in course of construction, and from a maze of reinforcing steel rapidly rising toward the uppermost rim of the canyon. These structures were later to serve as giant inlet valves for the outlet conduits and power penstock systems, and the placing of the seats for the mammoth cylinder gates was an important phase in their construction. Located at the ultimate high water storage level of the reservoir, the 2 spillways designed to act as overflow controls in the open bypass system were located one on each side of the river, upstream from the dam and within the reservoir area. Work on their construction progressed simultaneously with that of the dam itself. One of the most interesting and spectacular phases of the work was the fabrication and installation of the huge steel penstock pipes, forming the conduits for the power and pressure outlet systems. This work was performed by the Babcock and Wilcox Company of New York City, who erected a modern steel fabrication mill near the dam site to facilitate the undertaking. As the pipe units to be fabricated were of unprecedented size and weight, it was necessary to design, build, and install special machinery solely for this task. Provisions were made to manufacture pipe ranging in diameter from 8½ to 30 feet, from steel plate varying in thickness from 5/8 of an inch to 2¾ inches. As it was impossible to ship units of this size across country by rail, steel plate was brought from eastern rolling mills, and the entire process of manufacture, including rolling and assembling, was initiated and completed at the Boulder Dam plant. First step in the fabrication process, after the plates had been laid out to dimension, was the shaping of the edges to ensure the precision and accuracy of later steps in their manufacture. This work was done on a planing machine capable of handling a strip of steel 50 feet in length. The plates were then given an initial bend on a giant press operating at a pressure of 3,000 tons. This initial bending was necessary to avoid damaging the rolls when the plates, in the next step of fabrication, were rolled into circular form. The plates entering into the manufacture of the 30-foot diameter penstock pipe were fabricated through the initial steps of manufacture in 11-foot widths. These plates were 2¾ inches in thickness and were rolled into circular form by being passed through 40-inch vertical rolls until the desired degree of curvature had been obtained. One such plate represented a segment equal to 1/3 of the complete circumference of a finished pipe. Having been rolled to the correct degree of curvature, the 3 curved plates were joined to form a single ring, 30 feet in diameter and 11 feet long. 2 such rings were then joined end to end to form a shop unit 22 feet long. All joints were made by electric welding, and in forming the longitudinal joints, an automatic welding machine traveling on a chassis supported in line over the joint was used. As these pipe units were of a size never before assembled, it became necessary to design and build special machinery to accomplish many phases of the work. This was especially true in the fabrication of mitered rings to be later assembled into bend sections. The general usage of electric cutting and welding was applied not only to pipe sections, but to the manufacture of other fabricated units as well. A complete shop unit weighed from 150 to 184 tons, depending upon its design, determined by its ultimate use upon installation in the power penstock system. Circumferential joints were made by rotating the rings, making up a shop unit beneath an electric welding machine suspended above the line of the joint to be welded. Every foot of welded joint was subjected to a searching examination by X-ray and recorded on photographic film, which exposed even the slightest imperfections in the continuity of the weld. Samples of typically welded joints were subjected to severely rigid laboratory tests. calculated to produce a condition of strain far in excess of that to be borne by the joint under actual usage. The discovery of even the slightest imperfection was sufficient cause for the rejection of a complete unit. In marked contrast to the meticulous care and precision exercised throughout every phase of their manufacture was the actual size and weight of the pipe units themselves. Heavy-duty rigging of special design was required to handle the sections through the shop, and high-capacity cranes were required to move them step by step through the progressive phases of their manufacture. To equalize the terrific internal strains introduced into the plates by bending and the additional temperature strains incurred during welding, individual pipe sections were subjected to a temperature of 1400 degrees Fahrenheit in a gigantic annealing furnace. This temperature was induced not by the application of flame itself, but through the circulation of superheated gas. Shop processes were carried only as far as the production of the unit section. As these sections were to be joined to form a continuous penstock, provision was made to accurately accomplish this junction in the tunnels. To guarantee a satisfactorily tight field joint, the ends of the sections were machined on a mammoth vertical lathe, operating across the 30-foot diameter of the pipe. After a final inspection, the pipe section was ready for installation. A modern streamlined train passing through one of the huge tubes affords an interesting gauge for the comparative size of the units. The job of transporting the pipe sections from the plant to the dam site was in itself a tremendous undertaking. And to accomplish this work, a special road trailer capable of carrying 200 tons was designed and built. Caterpillar tractors furnished the motive power, as the trailer itself was not equipped with the means of locomotion. During handling, the conformation of the pipe section was maintained by rigid internal bracing. The movement of the heavy trucks was controlled by air brakes and power steering apparatus, with which the trailer itself was equipped. Upon arrival at the canyon rim, directly over the dam site, the unit was maneuvered into position for lowering into the canyon. To perform this task and to handle other heavy equipment, a permanent 200-ton capacity cableway had been swung over the gorge, its 6 3.5-inch track cables securely anchored into the rock of the canyon wall. The cableway was manipulated from a control tower overhanging the canyon, from which the operator commanded a full view of all its movements. The heavy hoisting machinery, controlled by synchronized motors, was the largest and most powerful of its kind ever built, as were also the track cables themselves, which spanned the canyon a distance of 1,256 feet at an elevation of 700 feet above the river from the head tower located on the Nevada side. Over the track cables traveled the carriage through which the hoisting and traveling cables were played. A specially designed heavy-duty rig, which became known to the workmen as the moonbeam, because of its peculiar shape and from which the pipe sections were suspended, was used in lowering the huge tubes into the low levels of the canyon while cradled in a sling of heavy steel cable. After all lashings were secure, the pipe section was lifted from the trailer to begin its slow and carefully controlled movement over the cableway, riding from the rim out into space, suspended 700 feet above its ultimate position. When the cable carriage with its tremendous weight of steel had been maneuvered into location over the intended landing far below, the hoisting cables were slowly played out and the pipe lowered under absolute control into the canyon. Here, a second specially designed car waited at the portal of the access tunnel to relieve the cableway of its burden and carry the pipe section underground to become a part of the extensive conduit system penetrating the cliffs on both sides of the canyon. With the workmen laboring in the tunnels far underground, the gargantuan task of placing the penstock pipes in position to form continuous conduits between the intake towers and the powerhouse and outlet works was accomplished. The separate units were hoisted into location with the aid of cables, and once placed in position, were joined with pressure pins to form a continuous pipe. While work on the appurtenant features of the Boulder Canyon project was in progress, an uninterrupted stream of concrete had been pouring into the forms of the dam from both mixing plants. Progress was curtailed only by the limitations of sound engineering and construction practice. Day by day, week after week, the top workings of the structure approached its full height of 730 feet, far above the crest of any other dam yet built by man, or likely to be built for years to come. Schedules established at the outset of the work were left far behind as the concrete of the dam narrowed toward its crest and the structure widened between its abutments, approaching the very top rims of the canyon. In June 1935, the dam structure itself stood completed, 2.5 years in advance of the time originally designated. In September of the same year, President Franklin Delano Roosevelt, voicing high praise for both designers and builders, dedicated Boulder Dam to the progress of the nation. As final construction work was completed, the impressive beauty of the structure became apparent. The roadway traversing its 1,300-foot crest forms a magnificent link in a transcontinental highway. The reservoir filling behind the dam was named Lake Mead in memory of Dr. Elwood Mead, late Commissioner of Reclamation, whose life work culminated in the building of Boulder Dam. The largest artificial body of water in the world, it extends upstream 115 miles into the lower reaches of the Grand Canyon, with a shoreline of 550 miles opening upon vistas unglimpsed by man until invaded by the gradually rising waters of the reservoir. Equipped with cylindrical gates which function as giant valves, the 4 intake towers serve as inlets to the 4 steel penstocks, supplying water to the turbines and outlet valves. Perched on shelves hewn into the canyon walls, they tower 403 feet to an elevation above the crest of the dam and the rim of the canyon. With a combined capacity of 400,000 cubic feet of water per second, the 2 spillways, located one on each side of the canyon upstream from the dam, will serve as high-level controls once the water of the reservoir has risen to its maximum storage elevation. Each spillway is equipped with 4 100-foot drum gates, acting through a vertical dimension of 16 feet. Water flowing over the lowered gates into the spillway basin plunges 600 feet down through the tunnels to re-enter the river downstream from the dam. The Boulder Dam power plant is built in 2 wings, one along each side of the canyon wall at the downstream toe of the dam. The first generator was placed in operation on September 11, 1936. Equipped with 17 generating units with capacities ranging 40,000 to 82,500 kilovolt amperes, this, the world's largest power plant, is capable of generating 1,835,000 horsepower of electrical energy when operating at its rated capacity. The transmission lines carrying Boulder Dam power radiate in a network from the dam with the major lines serving the Los Angeles metropolitan area. From the takeoff structure located on the roof of the powerhouse, the lines are taken up over the rim of the canyon into the switchyard above, where the most highly specialized and modern developments in the power transmission field are to be found. From the switchyard, the lines travel out across the desert, bringing light to the homes and cities and power to the factories of Southwest. From Parker Dam, 150 miles to the south, the Colorado River Aqueduct supplies the city of Los Angeles with the domestic and industrial water supply. While from the Imperial Dam, 300 miles to the south, the All-American Canal diverts water from the Colorado River into the rich agricultural districts of the Imperial Valley. And so Boulder Dam stands today, a modern colossus, shouldering the rock-ribbed walls of Black Canyon, stemming and controlling the floods, and bending the will of a hitherto ungovernable stream, the Colorado River, to perform the fruitful tasks of a civilization rapidly invading the limits of its last frontier.
Poor Barbara, not for her the carefree hours of happy play, nor the busy hours of work and study. What has happened to her that she lies there so hot and feverish, so weak and dizzy, so miserable with suffering and pain? Our body is just like a little country that has been invaded by an enemy army. But the enemy in this case is not big soldiers. This invading army is so tiny that it can be seen only through a microscope. Its soldiers are the germs of communicable disease. Some of these disease-causing organisms are so small that they cannot be seen even with the most powerful microscope. They are detected only because they can pass through the tiny holes of this filter. A communicable disease is one which can be caught from someone else. This means that the germs have to leave the body of a sick person and enter the body of one who is well. The usual gateway by which they enter is through the mouth or nose. How do germs make the trip from sick to well and thereby spread disease? They may travel by one of several ways. Coughs and sneezes, which are not protected, send germs in a direct spray. Kissing also gives germs a direct, short trip. The public drinking cup is a favorite means of travel. Water, as we find it in nature, may have harmful germs in it. If we drink such water without first boiling it, we are giving these germs a free ride into our bodies. Milk is the best food there is for us. But if it comes from unhealthy cows, in dirty surroundings, or is handled by people having a communicable disease, it can become a good conveyor of germs. Rats and some insects, particularly the fly, are of great help to germs of certain diseases by carrying them from filth to the food we eat. Thus you see that germs have several ways of traveling from the sick to the well. As individuals and as a community, we can do many things to halt this movement of germs and prevent the spread of disease. A healthful community must have a safe water supply. Here we see sedimentation and chlorination, a part of the process of water purification. In rural areas, a safe water supply requires a properly constructed well located on higher ground and at a considerable distance from the toilet. The purity of a city's water supply is further protected by the sanitary treatment of sewage. A series of processes renders the waste non-injurious to health. In rural areas, the problem of disposal of human waste can be solved by the building of a proper type septic tank. Or, if this is impractical, by building properly constructed sanitary toilets. Care in all steps of handling milk will do much to reduce milk-borne diseases. Cleanliness in the dairy, healthy cows, clean and healthy milkers, sterilized buckets, and cans so constructed as to keep out dust and flies all help to bring us safe milk so important in our lives. Pasteurization, which does not take the place of all these other precautions, is the one way to make sure that milk is safe. Anti-fly measures, particularly the disposal of breeding places, will help halt one of the most important ways by which germs travel. Tight-fitting screens are effective not only against flies, but also against mosquitoes. We can do much to prevent the spread of disease by keeping away from those who are sick. Common sense tells us to stay away from indoor crowds whenever communicable diseases are prevalent. Always call the doctor early whenever a communicable disease is suspected. Early treatment may lessen the severity of the sickness and halt its further spread. It is the duty of anyone suffering from a contagious disease to remain at home until the doctor feels it is safe for him to go out among other people. Some diseases, such as smallpox, diphtheria, and typhoid fever, could be wiped out entirely if each and every one of us took advantage of the time-proved protection offered by vaccination and preventive inoculation. One of our best weapons in preventing the spread of disease is cleanliness, which is particularly important when there is a communicable disease in the house. Certainly, cleanliness should be observed in all places where food is sold or served. All dishes used by the public should be sterilized. Our hands may pick up germs. The one act of washing the hands after going to the toilet and before eating is an invaluable health measure. The use of paper cups instead of common drinking glasses will help keep down the transmission of disease. We cannot keep all germs from entering our bodies, but wise old nature has placed within us natural forces capable of fighting the invading armies of disease. The better the condition of our health, the stronger this last line of defense against the invader. Building up this resistance depends upon a well-balanced diet which satisfies all the food requirements of our body. Outdoor exercise in the fresh air and sunshine. At least 6 glasses of water daily. And plenty of rest. At least 8 hours of sleep every night. Every step we take to prevent the spread of disease means increased happiness and greater living efficiency for all of us.